Swayam Prabha. Digital India. Educated India.
Welcome to the class. In today's class we will see about the steam engines. Till time what we have covered in last class was about basics of thermodynamics, and then we have seen what do we mean by Carnot cycle, and then what do we mean by Rankine cycle. And now today's class we are going to see for what does it get comprised for a steam engine, and then how different power sources are there, how much electricity is generated, and then what are the basically ways by which we can do some computations or calculations for steam engine. So this slide gives an idea for the world energy consumption, and it can be seen that world energy consumption is based upon various sources, which includes oil, coal, gas, nuclear and renewable. Renewable would have basically hydro, biomass, wind, solar. So these are the different energy sources which people across the world or countries across the world use for consumption, and this consumed energy would either get converted into mechanical energy as per the requirement, or may be converted into electrical energy as per the requirement. So or maybe it would be used for some industrial applications like drying. So the same situation across the world can be seen for India, where prominent energy source for India is coal, and then we have small and large hydro power plants. We will have further gas, nuclear and diesel engines for consumption of energy. If we see worldwide electricity consumption, the first slide was more about energy consumption, this slide is more about electricity consumption. So electricity consumption, the unit is kilowatt hour per year. We can see that it's a very big amount, where China is the lead country and India fall out to be the third country as per this table. So we need largely electrical energy, and that electrical energy would get further utilized for various applications. And what has these slides of energy and electricity relevance with our steam power plant? Since steam power plant, as what we know, is a thermal power plant, where thermal energy, where if we go back to last slide, then among these sources of energies, nuclear or coal or oil are the basic sources on which the thermal power plant, which is a steam power plant, it runs. So our steam power plant needs energy, and that energy would be extracted from either coal, oil or nuclear. And then we largely are interested in conversion of that energy from coal or oil or nuclear to electrical energy. So this is what the general idea about how much electricity is basically required for countries like India when we see the per year electricity consumption. Now we come back to our topic of discussion on steam engines. Steam engines are not the topics of discussion which have recently started. It is known from 1st century AD itself. The Hero's engine was the name for the Eole piles which are shown in these figures. So basically Eole piles are the bladeless steam turbine, where you can see that there is a drum which is attached with two inputs of the steam from a boiler, where we have a bottom half circular, half spherical drum. It is supplied with heat. This is water vaporizer, and it is supplied with heat by burning coal. So water would get evaporated, and then it goes inside this sphere or spherical container through the two limbs which are shown in these two figures. Once vapor comes into the spherical drum, vapor would get ejected in these two jets, and then accordingly by reaction this spherical drum rotates. So this is the principle of Hero's engine or Eole pile, and this is the basic idea where it has started, that there can be steam engine for generating initially mechanical energy and then onwards for electrical energy. It was made initially so that it can be used for sailing the ships or boats. Based upon the concept of steam as a working medium for having the rotary motion generated, we can see that there are very big power plants, and one such big power plant is in Taichung, and then this is Taichung power plant, and then this is one of the largest power plant in Taiwan. It generates electricity of around 5500 megawatt, and it has a drum type of boiler with single reheat steam turbine. So the idea of what can be the largest amount of electricity generated by a steam power plant we can get over here, that one of the largest steam power plant generates 5500 megawatt of electricity, where coal is working fuel for this. If we come back to India, then in case of India we have one such very large steam power plant called as Vindhyachal Thermal Power Station, and it is in Singrauli district of Madhya Pradesh. Its capacity is 4760 megawatt and it is operated by NTPC. So as what we can see, that we need when electricity, then the power plants produce electricity of larger power plant sizes have electricity generation of few megawatts. But it is not only electricity which is the only need of ours. As I said, we might need mechanical energy also to be generated, and in such case steam can be acting as a good working medium. We can see that steam has been used as a source for generating mechanical or having drives where mechanical energy would get utilized, where first such attempt was to have locomotive which ran between Stockholm to Darlington in UK in 1825, where steam based locomotive was used. Similarly, as in case of world scenario, we had Indian locomotive also ran between two stations in Madras in 1837. First such train which had its operation using steam ran between two stations around Mumbai, and it took place in 1853. So as what we can see, that steam can be a working medium where we can generate electricity, or we can as well have mechanical power generated. Then how does steam can act as a source where we can use the energy from the steam to generate mechanical energy or mechanical power and hence electricity? We have seen in last class that a steam power plant is comprised of four parts. First part is pump, where steam would get low pressure to high pressure pumping in the device which is pump. So steam would get pumped from low pressure to high pressure. Then this process basically is isentropic process. Then steam would have basically heat addition in isobaric sense in boiler in the process 2 to 3. Then we have expansion of the steam in the turbine in the process 3 to 4, and then the device is turbine. And then we have heat rejection of the steam, and that process is 4 to 1, and then that device is condenser. So these four parts, pump, boiler, turbine and condenser, comprise a typical steam power plant, and then there are such four processes. If we see such four processes, then first process is isentropic compression. We can see that there are three diagrams in this. The first diagram on left hand side is PV diagram, then we have TS diagram, and then we have HS diagram, which shows the Rankine cycle. Process 1 to 2 is like this. On PV diagram it is a vertical line, on TS diagram and again it is a vertical line in HS diagram. Then this process is isentropic compression. Then we have process 2 to 3, which is isobaric heat addition. Since the process is isobaric, pressure is constant. In PV diagram, pressure would constant again in TS diagram, but this constant pressure line is occurred in TS diagram in sensible parts, and it is a horizontal line in latent part. As what we know, practically we have to sketch a dome first for the drawing of steam power cycle, which is a Rankine cycle. Then this is again a curved line 2 to 3 on HS diagram. Then we have process 3 to 4, which is isentropic expansion. Expansion where volume increases and pressure decreases. This process is like this in PV diagram. It is a vertical line in TS diagram, and it is again a vertical line in HS diagram. And then we have process 4 to 1, which is isobaric heat rejection. Pressure is constant in the condenser. So it is a horizontal line in PV diagram. It is again horizontal line in TS diagram, but it is an inclined line, curved line in HS diagram. So what we can see that we have to plot TS, PV or HS diagram for better understanding of a steam cycle thermodynamically. And in this process, we should understand that in case of TS diagram, we have constant pressure line, which is 2 to 3, which has intermediate one of the steps where latent heat is supplied in the boiler. But before that, we have supply of sensible heat where we do not have horizontal line in TS diagram. But heat rejection is completely latent heat in case of condenser. So it is a complete horizontal line in case of condenser. But when we see HS diagram, then HS diagram has basically slope which is different from the TS diagram. So we have a different line which is 4 to 1. Having said this, we know now how to plot the diagrams in TS, HS and PV for a Rankine cycle. This is a typical TS and HS chart from the steam tables. We would need such a steam table to be used for our example solving or for usage of it when we are dealing with steam turbines or a part of a steam power plant. Then we want here onwards to estimate the properties of practical steam power plant or Rankine cycle. This is our Rankine cycle, very typical Rankine cycle, where we are saying that we have process 1 to 2 in the pump, where we are having work input, which is a pump work. Process 2 to 3 is a heat input in the boiler. So we will say it is a pump here, it is a boiler here, it is a turbine here, and it is a condenser here. So these are the 4 parts which are dealing with the steam power plant. Now what would happen in case when we are working with steam power plant? The most general things which we would be knowing is a condenser pressure, which is P1 and P4. Line P1, line process 4.1 is a isobaric process, so it is having pressure either P1 or P4, rather which is P1 is equal to P4, and this pressure would be known to us. In general, whenever we are having steam power plant, the condenser where heat is rejected from the steam and water in vapor state would get condensed to liquid water. So that heat rejection would happen with the use of natural resources like river or ocean. So atmospheric condition or atmospheric temperature remains the temperature at which heat would be accepted by the ambience. So this pressure basically corresponds to the saturation pressure corresponding to the atmospheric temperature. Then what quantity we would be knowing is P2, rather P2 is equal to P3, and P2 and P3, they are the boiler pressures, and we would be having idea of this boiler pressure. Steam power cycle is also called as a constant pressure cycle, where heat addition takes place in a constant pressure or heat interaction takes place in a constant pressure sense. So both the constant pressure lines would be known to us, and then what would be known to us is a condition at 1. Entry to the pump means we would be knowing T1 and P1. So these things which would be known to us, and using those known things we would have to calculate efficiency, performance or other heat and work interaction. So at point 1, point 1 is basically exit of the condenser or entry to the pump. It is the saturation point of the liquid water, and that saturation point has pressure P1 and it is known to us. Point 2, from point 1 we have to draw a process which is isentropic process, which is 1 to 2. So entropy at 2 is known to us, which is same as entropy as 1. So the device involved in this process is pump, and medium handled by the pump is liquid, and then we can calculate pump work, which is H2 minus H1. We should remember the formula or the method of interaction of heat and work what we would have discussed about open cycle, where we have used steady flow energy equation, where we said that Q minus W is equal to summation of energies like enthalpy, kinetic energy, potential energy at the inlet, or summation of all inlets of these energies minus summation of energies like enthalpy, kinetic energy and potential energy at the outlet. And in the pump we are neglecting kinetic energy, we are also neglecting the potential energy at between the inlet and the outlet. So it turns out that heat and work interaction would have balance due to enthalpy change, but pump would have process so fast that we can neglect the heat interaction in pump. So basically pump work turns out to be the enthalpy change between inlet and outlet. So this is the discussion for state 2. Then we have state 3. At state 3 we have process point 3 would be obtained from 2 to 3 process, which is a isobaric heat addition. The device involved is steam generator. The material handled is basically a two-phase material, where initially some part would be liquid from 2 to saturation, liquid saturation point. Then we would have partially wet steam till this point, and then we get dry saturated steam at this point, and there onwards we have only vapor state in this sensible part. So, but in all, steam generator or boiler would handle two-phase flow, which is liquid plus steam. The amount of heat added into the boiler or steam generator is equal to the rise in enthalpy of water, which is H3 minus H2. The process P has constant pressure, so we have P3 is equal to P2, and as per the TS diagram we can see that this is the maximum temperature in the cycle. So T3 is equal to T max. Having said this, we can enter to point 4, and this point 4 is obtained from the process which is 3 to 4, that is an isentropic expansion. Device involved is turbine. As per this diagram, turbine has only steam, which is a vapor state, but it might not be always true. We might have an expansion of turbine like this, where this part of turbine handles wet steam also. So turbine in general can have a two-phase flow, where it would handle steam plus liquid. Same, turbine is a work producing device, so the work done by the turbine is across the enthalpy drop of the steam, which is unlike as in case of pump, where pump is a work input machine which needs input of the work, and then due to this we have rise in enthalpy of water from H1 to H2. But in case of turbine, we know that it is an isentropic process, so enthalpy at 4 is entropy at 4 is equal to entropy at 3. This is an isentropic process. Then once we can know how to estimate all the corners of the cycle like 1, 2, 3, 4, or maybe the corners corresponding to saturated conditions. Once we have understanding of this, we can find out performance parameters of the steam power plant, and those performance parameters initially would include pump work, and we have said that pump work is H2 minus H1. Across the pump we have enthalpy gain for the water, and then we have heat addition in the steam generator, which is Q in, and in the presence of this Q in, enthalpy of the water rises from H2 to H3. Then we have turbine work, which is H3 minus H4. Turbine produces work, so enthalpy of the water decreases. Then we have heat rejection process in the condenser, and then we have heat rejected is equal to H4 minus H1, where enthalpy of the steam or water decreases. Then using these calculations we can find out net work, which is gained by us in the form of mechanical energy. Then that work is W net, which is equal to turbine work minus pump work, but we know that turbine work is H3 minus H4 and pump work is H2 minus H1. So net work is H3 minus H4 minus H2 minus H1. Then we can find out efficiency. The classical formula for efficiency is W net upon Q in, but W net is Q in minus Q out. So where Q in minus Q out is W net, and then we have Q in minus Q out upon Q in is efficiency. So efficiency becomes 1 minus Q out upon Q in, but we know Q out, and Q out is H4 minus H1 and Q in is H3 minus H2. Knowing these enthalpies at these 1, 2, 3, 4 points, we can find out enthalpy efficiency of the steam power plant. Then discussion on pump work. So here we see that in general pump work, as what we can see in this diagram, pump work is H2 minus H1, where turbine work is H3 minus H4. So as what we can see that pump work is much less than turbine work, or in general pump work is less than turbine work. So pump work is negligible in comparison with turbine work. Here our problem is that we have to estimate still what is the pump work. So we should know how to find out WP. Although we know that WP is equal to H2 minus H1, but we said that we know H1, and H1 corresponds to saturation enthalpy of liquid at pressure P1. It is a saturation enthalpy. But how to find out H2? We would have steam tables, but steam tables would not generally deal with liquids. So steam table would deal with vapor. So H2 is an unknown parameter for us. So to estimate H2, we have to use different tactics. And in that case, we know that as per mixed or combined first and second law, we know that TDS is equal to DH minus VDP. Okay. In the pump, we have isentropic process, so this is equal to 0. So DH is equal to VDP, and we know that if we integrate it from process 1 to 2, this becomes H2 minus H1 is equal to integral 1 to 2 VDP. In case of pump, we are so close to the saturation point, and further we are handling liquid as what we have said. So for liquid, specific volume or the density, they are constant, since liquids are incompressible matters. So we can take this V to be constant. So we will have this V into P2 minus P1, and as what we discussed in earlier slide, we know boiler pressure, we know condenser pressure, and then we should know V, then we are done and we can find out WP. So this V is practically considered as any specific volume corresponding to the pressures P2 or P1, and then this pressure what we are talking about is P1. So what we can say that this is equal to V1 into P2 minus P1. This can be V2 as well, since it is not changing much in the process of pumping. So we can take any specific volume which is a saturation liquid specific volume, and then we should know only delta P, and then we can find out pump work. This is a steam table. So in this course we should know how to use steam table. So this is a particular case of a steam table, and this part of steam table is called as saturated temperature table. So this is for water. So this is a temperature part of the table, where first column belongs to temperatures. So we can see that there are many temperatures given, and then these are the properties of steam which are given in the steam table, and at those temperatures the things which are given as saturation pressure, saturation, we have a vapor, saturation, we again have enthalpies given, and we have entropies given. So we have specific volume, we have internal energy, and we have enthalpy, and we have entropy, and these things are given in a steam table. So corresponding to temperature we have saturation pressure, and then we have specific volumes, and this first specific volume is saturation volume of liquid, second is saturation volume of vapor. So we can see that if we at all we change the temperature, saturation temperature, there is not much change in the specific volume. That is what we were discussing, that in the pumping process we can treat specific volume as a constant. After this part we have other part in the steam table, and that other part is basically pressure part in the steam table, where instead of saturation temperature, saturation pressures are given in discrete formats, and then we can use a particular saturation pressure and we can estimate same quantities which are specific volume, internal energy, enthalpy and entropy. Then we thus can find out all the corners of the Rankine cycle using steam table. We have to watch out with the units which are given. Then the third part in the steam table is saturated, supersaturated conditions, which are the conditions like conditions in the intake to the turbine. Here we generally would be given supersaturated, we would be given that there is a temperature, there is a pressure, and for one pressure there will be different temperatures given, and in the superheated part we will have first saturation temperature. Corresponding to saturation temperature we are given with specific volume, internal energy, enthalpy and entropy, but these things are also there in the saturation pressure or saturation temperature part. But after that, if we have temperature which is more 50 degree, 100 degree Celsius, 150 degree Celsius, so if those temperatures are superheated temperatures, then what would be the corresponding value of specific volume, internal energy, enthalpy and entropy? They can be found out from the superheated part of the steam table. So this is how we can make use of steam table, and then we can solve our examples, or we can deal with a particular situation in the steam power plant. Then we have discussion about heat addition. We said that process 2 to 3 is heat addition, as what it can be seen here. Process 2 to 3 is heat addition process in the boiler, and then but we know that this is the process 2 to 3. This is process basically. So the process of heat addition, as what we can see, it is getting done in the boiler, where 2 to 3 is the process of heat addition in the steam power plant. But the same process, when we represent it in the TS diagram, we said that 2 to 2 dash is a partially one part of heat addition, then 2 dash to 2 double dash is second part of heat addition, and 2 double dash to 3 is third part of heat addition. So here 2 to 2 dash is done in economizer, 2 dash to 2 double dash is done in a steam generator, 2 double dash to 3 is done in a superheater. So the heat which is QH3 minus H2, which is added in the boiler, gets added in 3 parts. So this is one part, this is second part, and this is third part. So this is called as Q economizer, this is called as Q evaporator, and this is called as Q superheater. So we have Q economizer, which is H2 dash minus H2. So Q, small q economizer is fraction of heat added in the economizer out of total heat addition. Then we have Q evaporator, which is H2 double dash minus H2 dash. So fraction of heat added in the evaporator is Q evaporator divided by total Q in. Then we have heat added in the superheater, where H3 minus H2 double dash is Q superheat. So fraction of heat added into the superheater is Q superheater divided by total amount of heat added into the superheater. So we know how to find out pump work, and then we should also know, apart from the fact total amount of heat added, how much is the fraction of heat added into the different parts of the steam generator or boiler. This decomposition of heat addition is practically helpful, since Q economizer practically deals with sensible heat for liquid. This evaporator deals with latent heat, and Q superheater deals with again sensible heat, but this is for vapor. So we are decomposing the total heat into different parts. These 2 points we would be knowing from the steam table. So this steam table would tell us these 2 points. This point we would have known it from the some constraints, and then this point we have found out after the assumption of pump work with V into delta P. So thus we could know all the 3 points, and then we can find out what are the different fractions of heat added in the different parts. So then we have efficiencies. Then we have source efficiency. Source is something like coal or oil, where source efficiency Q in upon energy released in combustion. This is source efficiency. Then we have cycle efficiency, as what we have seen. Cycle efficiency is W net upon Q in. Then we have mechanical efficiency. Mechanical efficiency is amount of power measured at the turbine outlet divided by Q in. This is the brake power. Then we have generator efficiency, which is generator power, electrical power generated divided by power measured at the turbine outlet. And then we have auxiliary efficiency, which is net auxiliary power output or power required for auxiliaries to run divided by generator power. And then we have overall efficiency, which is multiplication of all efficiencies, which is source efficiency, cycle efficiency, mechanical efficiency, generator efficiency, and auxiliary efficiency. These efficiencies have their ranges, which are 0.92 for source efficiency, 92%, cycle efficiency is in general around 40%, we have mechanical efficiency, which is around 95%, we have generator efficiency again around 93%, auxiliary efficiency around 95%. So overall efficiency for a steam power plant turns out to be 34%. So this is all discussion about efficiencies of the thermal power plant. So here basically these efficiencies are calculated under the assumption that the processes like 1 to 2, which is pumping process, heat addition, isentropic expansion or heat rejection, that all the processes are ideal. So based on these we have found out efficiencies, and these efficiencies turn out to be the performance parameters of the steam turbine. So here we end our discussion for today's class, where we started with steam engines, then we saw how to find out different corners of the Rankine cycle, and then we headed towards how to see the steam table and how to make use of the steam table for further use to solve some examples, and then we went and discussed what are the different ways by which we can find out pump work, what are the different factors or what are the different parts of a boiler where heat is added in different parts, and then we have seen what are the different performance parameters. Rest of the things about steam power plant we will see in the next class. Thank you.